Hello everybody, my name's Chris. Thanks for coming. And today I'm going to be talking about some details about paint and compositing that I think are interesting, complicated, maybe a little sad, but it's the truth about how the web seems to work, or does work actually. And they're things that actually the paint team has in many cases learned over the past year that we didn't really know actually before that. So if you were at the last BlinkOn, I talked about slimming paint, which is the main project we're doing to refactor the paint system step by step into a place where we can solve a large class of problems that are similar to the ones I'll present today. I'm not actually going to talk about slimming paint today. It's really going to be about what are the semantics of paint and how do those things result in a complicated paint system and also a complicated compositing system that tries to accelerate that. So you'll see at the beginning that maybe I'm starting off with concepts that seem simple, but it's going to quickly get more complicated. Also, please feel free to speak up and ask questions along the way. If I'm going too fast or something is not understandable, please let me know because like I said, I expect these things to get a little bit complicated and they're hard to reason about. Okay, so let's get started. Oh, and also, by the way, Paint Dev is our mailing list, but also I'd like to thank members of the Paint and Compositing team for their input in like figuring out the things that we know today and helping me with these slides. So paint order. Paint order is the most fundamental thing about what is going on with paint. As you probably know, the elements on a page paint in a particular order. And by default, that order is basically the order of the DOM tree. And there's also a parallel tree, if you're not familiar with it, called the layout object tree, which for the purposes of this talk, you can think of as equivalent to the DOM tree. So there would be one layout object, which represents the position and style, let's say, of like a div or something like that. That corresponds to the exactly equivalent DOM element, and let's just say they all have the exact same tree structure, which is generally true for the kinds of elements I'm going to talk about here. So here's an example, just a very simple example, of an element A, which has two children, B and C. As you can see, all of them are position relative and have a certain width and height, and then I have positioned them so that even though they're children, there's this stacking appearance going on. So you'll see that, like I said, by default, the paint order is tree, so that the thing at the top, the blue one, paints first, and then the green one, which is the first child, and then the red one, which is the third child. So in terms of the perspective of actually implementing paint, which is the perspective I'm hoping to get across today, first you would, in your algorithm, go to the root layout object, or the root element. Layout object is the same as element in this talk. And paint it into, let's say, a bitmap. And then recurse into the children, and the first child is the green one, so then you paint a green rectangle on top of it in the bitmap. And then you paint the third one, the red rectangle, on top of the green rectangle, which was on top of the blue rectangle in the same bitmap. And now you've drawn all the things onto the screen in this example. So this is very simple, and in many cases, when you don't have anything to do with compositing or extra effects, this is actually sort of what happens in the paint code. And because of implicit painting and other advances, it doesn't actually raster it that way, but you can still think of it that way in the simple cases. I'll point out here that there are actually a number of other things to do with paint order that I'm not really going to go into today because I'm talking about other aspects. For example, there is such a thing as paint phases, where you actually do multiple recursion passes over the tree in order to paint the backgrounds and the border before the text and things like that. So yeah, I'm going to skip that. Okay, so again, thinking of it in terms of recursion, you start at the root, then you paint A, then you paint B, paint C, and then you're done. Okay, so let's go on to a second example, z-index. As you know, z-index is a thing you can put on a position relative or position absolute or position fixed element that pushes it forward or backward in the relative paint order of the things around it, let's say for the moment. I'll make that more precise in a minute. So in this case, here I have a z-index -1 that I've put on the B div, which means that the green thing, which is the B div, is pushed to the back. So how does that actually work? So obviously, in the order of paint, you're going to paint the green, and then, sorry, I got that wrong. That blue one should be on top, and then the red. So pretend it was on top. So let's look at it in terms of recursion structure of what's going on. So you start at like the root, or like the thing which holds on to the layout object tree, and then somehow you recurse into B, and then A, and then C. So notice here that we've already encountered something that's a little bit strange from the point of view of a recursive painting algorithm, which is that this topology of this tree is not the same as the topology of the DOM. And so somehow, with respect to paint, there's actually a different tree going on. And the way this is actually implemented in Blink is not using a different tree. It's using sort of an implicit representation of that tree by keeping track of what are the things in the z-index order that are your children, if you have any z-index order, z-index children. So, and there are various other complexities that will layer on top and make everything more and more complicated, and then you can, I hope, start to see why the painting code is much more complicated than it would first appear, and why like projects like semi-paint even become necessary, and so on. So just keep that in the back of your mind, and try to think to yourself of ways in which you could possibly implement this kind of thing without creating parallel trees or some other fancy thing. Okay, so I'm going to build up some observations as we go along. The first observation is the one I just said, that the paint tree topology is not the same as the DOM tree topology, or the layout object tree topology. So let me talk about why you wouldn't just like change the tree topology and call it a day. The reason is that things like clipping and scrolling actually apply to DOM children. When you put an overflow hidden or overflow scroll on an element, it applies to children. It doesn't apply to somebody else. So, so you have a situation where the tree topology of paint is different than that of the DOM's tree topology, but nevertheless, the inheritance or the way that effects nest with each other wants to be more like the DOM, because that's the way that CSS works. So in this case, we have an example where the element A has overflow scroll added to it, and otherwise it's the same as my first example. And that's and I've actually in the example scrolled the green and red rectangle up a little bit to demonstrate the scroll. And so that's why the final thing has the same size as the blue rectangle, and it's not getting bigger because the things are clipped off. Okay, so let's think about how to go about like implementing the sequence of commands to draw this thing into a bitmap. So first, like because the blue thing is first in paint order, you paint it, okay, fine. And then now you're going to recurse into it, and you know it's scrolling. So the strategy I'm going to demonstrate is one where you sort of draw the things below them as if they didn't know they were scrolled, and then shift them and scroll them afterward. So let's just make a dotted line to represent the coordinate space of the blue div. It doesn't actually represent any painted output. It's like conceptually this is where the blue thing is, and then we're going to put those other things in a space that's different than that. So the green rectangle positions into a space which is offset from the dotted line rectangle because of the top left 25 pixels, and likewise the red rectangle. But now we need to like get those things into the parent space. So you scroll them by however much the user has currently scrolled, or maybe there's a JavaScript scroll or something like that, and then you cut it off to clip it, and then now you're done with the children, and then you can just layer those two on top. So you can see here that like somehow we need to have like made a thing and then be able to cut off the pieces of it and then lay that on top of something else. So in this case, A common way to implement this, if you were just to do it directly, would be to just make a sub-bitmap and start messing with that. And then when you need to clip it, you cut it off, and then you draw it on top of a second bitmap. And as I'll explain later in the talk, variations of this, using more and more advanced techniques like GPUs and things, are actually what browsers really do. Okay, containing blocks. Containing blocks are super confusing. So what is the containing block? For just a regular old div, the containing block is your parent. We'll see in a few slides what containing block is all about, but let's just define it first. So the containing block of C is B, and the containing block of B is A. Okay, that was easy. Let's go to another example. Let's say we put position relative on C. So in this case, the containing block of C is still B, because that's the way it's defined for position relative. There actually are reasons why, but I won't go into them right now. And the same thing, obviously the containing block of B is still A because they're unchanged. So what if you put position absolute on C? So the containing block of C, in this case, so I actually put a position relative on A as well. So the containing block of C is actually going to be A, because the containing block of an absolutely positioned element is defined to be the nearest containing positioned ancestor. There actually are a couple of other corner cases, but just think of it as like the nearest containing positioned ancestor, meaning position relative, position absolute, position fixed, or in the future, position sticky. And for position fixed, suppose we change that position absolute to a position fixed. In this case, the containing block is the root HTML element, which is not really pictured here and is kind of implicit. So the fixed position element's containing block is always the root, because fixed position things position themselves relative to the actual screen that your web page is drawn into, not any particular subdiv. Okay. So what is the point of all this? So containing block comes into play in Paint when you are thinking about whether or not particular scrolling or clipping applies to an element. So a positioned element is only clipped or scrolled by something that is either its containing block, or its containing block's containing block, or its containing block, containing block's containing block, and so on. And this is called the containing block chain. So you're only clipped or scrolled by an element that is on your containing block chain. So regular divs are always clipped and scrolled by anything that has an overflow scroll or overflow clip or something, or a clip CSS that's in its ancestor chain. And a position relative also is the same. Position absolute is not clipped by anything except unless you either the thing with overflow scroll has a position on it, or there's something in between, because it makes it the containing block chain. So in this case, A is intentionally chosen not to have position, but it has overflow scroll. B is position relative, C is position relative, D is position absolute, and E is position fixed. And you've seen that I've interleaved the position relatives and the position absolute, position fixed ones. So D will not be clipped and will not be scrolled, and E will not be clipped and will not be scrolled. Nevertheless, paint order still applies. What this means is that you will have things that are interleaved with each other that need to paint on top of each other as normal, but when you go to like clipping and moving them around, sort of like after the fact, different effects apply. And this can get super crazy. So let me just like, instead of trying to like make a fancy diagram, I will just show you this example, which hopefully will load. So it's a little small, I apologize, but you can see that the, is this big enough? Maybe it's not big enough. Let me try to make this bigger. How about that? So you can see that the green and the red are scrolling, but the blue and the purple are not scrolling, because those are the position fixed and position absolute. And like the purple one is sandwiched between the green and the red, even though it's not being clipped and not being scrolled. So some people call this this class of example like the Escher effect example. There's a Simon Fraser example that's gone around the web that's basically a variant of this. So you can see here that this is a little wacky. And if you can imagine strategies for like efficiently caching contents of scrollable areas and things, you can see how this is like super annoying and difficult to implement because like what's going on? My brain's about to explode. Okay, so let's go back to the slides. All right, so so what's one way to possibly like think about painting this thing? So the orange one, which one is orange? Position absolute, right. So the orange one is going to be positioned. The green one is going to be clip, scrolled, and positioned. The purple one is going to be positioned, and the red one is going to be clip, scrolled, and positioned. So in general, the only way to correctly paint, or like the straightforward way to correctly paint this, is to like do all of them independently. Clip, scroll, and position them all independently into independent bitmaps, basically, and then at the end, lay them on top of each other in the correct order. And so, you know, we'll see in a few slides how, you know, who knows how to composite this? We'll have to think about that. Okay, and so I'll just point out that containing blocks are different than stacking contexts. You might have thought like, oh, maybe if only it had a stacking context, the world would be a better place. It's actually not true. For example, if you put opacity, which actually causes a stacking context on the scrolling thing, the problem still happens because stacking context only protects you against Z-order things, not containing block things. Okay, so let's add some more observations to our list of like things that make painting and compositing trickier than you would think. Clipping and scrolling and containing block in combination make for weird complexity. And stacking contexts don't fix that particular problem. Okay, so opacity. How do you apply opacity? This seems pretty straightforward. Like I mentioned, opacity creates a stacking context. Yeah, so let's go through this example. So here we have opacity on the root thing, which means that all of the divs should be painted not as with some amount of transparency. So in this case, it seems straightforward. All you do is you paint the three things in order, and then you like apply an effect that changes the transparency of those three after they've been put on top of each other, and there you go. You have the resulting output. So here's some more observations. Some things apply to groups of elements. So we saw earlier in the clipping examples that a clip applies to groups of elements, and that therefore maybe we can apply the clip once after we've drawn all those elements, but maybe we can't in cases where the containing block disagrees. Same thing for scrolling. And for opacity, we can also apply it to groups of elements. The thing that seems promising about opacity is this containing block thing doesn't affect how opacity applies. So maybe all these weird problems I referred to are just for clips and scrolls. Unfortunately, we will see that that's not true. It actually affects all of them, and I'll explain how in a few slides. And also, like, we're starting to see that maybe there's like some clever caching opportunities to keep around these intermediate bitmaps in cases where like divs below didn't change, but the div above is animating its scroll or something like that, or animating opacity. As you might know, Blink is good at animating opacity in cases where we can do it with compositing. Rounded corners. Rounded corners are super awesome, and they're all over the web, and they're more complicated to implement than you might think. So here I've just taken that previous example and I put rounded corners on the blue thing. So to implement that, you do all these things that I mentioned earlier about drawing them, positioning them, and clipping them for the children. And then you might make something called a mask, which is like an image that's black, where you're allowed to draw the pixels from the children, and white, where it's clipped out, or the opposite. You just have to choose one of the two. And then you intersect the clipped thing for the children, the bitmap for the children, with the mask, and the result is that you have rounded corners. So I'll just note that this means rounded corners require you have to have this extra mask bitmap going on. And this is different than rectangular clips, because computer graphics is, or just like, you can see from like the properties of rectangles that it's easy to cut things off in straight lines, because it's easy to make 2D arrays in memory. It's easy to think about things in terms of bitmaps that are square. And likewise, GPUs have all the same kind of optimizations. But rounded things, or things with arbitrary shapes, are not like that, and so you have to do extra things to explain how to cut it in a curve. Okay, so compositing. So compositing is basically the same thing as drawing things into bitmaps, except that you are putting them in textures in the GPU, which is the GPU version of what a bitmap would be in regular old memory. And then the GPU can also do certain operations for you that are parallelizable very much more easily. So for example, in this opacity example, let's suppose that A was composited. In Blink today, you would have to put an additional parameter on it, like will change transform or something like that, to tell Blink you should go ahead and store the result of drawing those sub things into a texture in the GPU. But if you did, then what would happen is that you sort of have this like tree inside of a tree. So like the thing inside of the blue element are drawn just into a bitmap, let's say, just with commands that draw into a bitmap. And then those are put into a texture, and then we apply the opacity using an accelerated composited implementation of opacity. So that would be like, you would write a shader, an OpenGL shader, say, or something like that, that would just change the color to change the transparency of all the pixels. And the reason you do this is so that you can animate the things that are like the things like opacity without having to redraw the content below, and do it all very efficiently, because GPUs are good at this sort of thing. Okay. So for rounded corners, here's how you can do it using the GPU. It's basically, like I said, the GPU version of the same thing. You go ahead and you make your mask by making an actual bitmap, basically, and you go ahead and you make your clipped thing, and you can actually implement a thing which does a masking intersection pretty easily using a GPU accelerated program or shader. And so this is how, for example, a scrollable thing how in Blink you can do a hardware accelerated scrollable area that has rounded corners efficiently without having to redraw things, because it keeps around that mask, and then the scroll and then application of the mask is all done very efficiently. So in this case, you have two new concepts. One is called a layer, a composited layer. So here, the term for the thing that's in that dotted rectangle is basically a composited layer, and the mask is also essentially a composited layer. And then in order to draw those to the screen, you can't, in this case, just draw them directly to the screen. You need this intermediate bitmap, which is what I mentioned earlier. For some of these effects, like rounded corners or things, you need to like draw into an intermediate thing and then put that thing into pixels onto the screen. And so here, there's an intermediate surface or render pass, or to represent the combination of, to represent the thing that is the intersection of the mask and the stuff below it. Um, and so these surface concepts are important because in order to implement some effects correctly and efficiently, you need to introduce additional intermediate bitmaps. And the more intermediate bitmaps you have, perhaps the more inefficient the system becomes, because in order to draw to the screen on every frame, even though you've cached the actual contents of the div, to draw them, you have to like send things up through these intermediate surfaces. Okay, so compositing is like painting except on the GPU, and it takes advantage of certain things that are awesome about GPUs. So let's get into the pipeline. Now that there are a bunch of things that we now know about sort of how painting works and sort of how compositing works. So in Blink, right now, the pipeline is Blink and the compositor together, thought of as one pipeline. It starts with compositing, which is you take the layout object tree and you try to decide which pieces of it go into which composited layer. There's always going to be one composited layer for, let's say, the document, but you might want to have more of them in there in order to like do fast scrolling or be able to rotate the transform of a thing or animate the opacity. So somehow you have to decide this. And of course, changing the way that works is the subject of Slimming Paint. But regardless of whether or not Slimming Paint is present or not, you still have to decide what content goes into what composited layers. And then there's invalidation. Invalidation is when you decide whether or not a layout object has changed materially from the last frame, and that therefore you need to like execute its draw commands again. For example, if you change the color of a div, you're going to have to draw that div again, right? So that div would be invalidated for Paint. And so the output of Paint invalidation is actually two things. One is that you've marked all of the objects that need to be painted again. And the second is that you have computed the areas of the various compositing layers that need to be drawn again into bitmaps or rastered. So Blink actually has to go ahead and compute the positions of all of those objects in the space of the composited layer that they belong to. And then the list of all those things that have occurred are stored off so that later on in the pipeline, things can be rastered. So then there's Paint, which is the process of walking over the tree in the order I sort of described in cartoons earlier in the presentation to execute all these paint commands. And some of these things to do with like storing off a bitmap and painting it into another bitmap and cutting things into pieces and positioning them actually is written down in terms of like a sequence of commands here. And we call this command a display list. So that this display list has commands like draw rectangle and draw a run of text and stuff like that. It also has commands like make a new bitmap, start drawing into that, and then when you're done with that bitmap, draw it into another bitmap. Save layer and so on. So after that is tile rastering. So each composited layer, as you probably know, is divided up into a number of tiles, which are like usually square regions of 256 pixels. And what we do is we take the display list and figure out for a particular tile which commands in the display list apply to that tile so that we don't have to run all of them, and then just run them in sequence, and then take the resulting bitmap and size it, and cut it off at 256 pixels, and then that's the tile. So there are multiple strategies for tile rastering. The simplest one, or not the simplest one, like there are two general categories. One is software rasterization, and the other is GPU rasterization, which is a new thing that we're trying to roll out more and more in Blink. So the difference between software and GPU rasterization is merely whether or not they take advantage of specialized GPU hardware to do certain things a little bit faster. Really, what is actually being done is essentially the same. It's running a computer program that executes those commands and outputs a bitmap, or a texture is really the final output. So if it's software rasterization, you run a computer program which outputs a bitmap, and then you copy that bitmap perhaps into a GPU texture. And in the case of GPU rasterization, typically, or I guess always, the output is directly already in the texture. So that's one of the ways in which it saves time. And then there's generation of surfaces, render passes, draw quads. So this is like those list of things that you have to do in intermediate steps in order to actually get to the screen, even after you've already rastered all of the tiles for all of the composited layers. So it's still like not O of 1 work to take the composited layers and bring them to the screen. You have to apply these sequence of things, such as intersecting with a mask layer, such as clipping and transforming and moving things around, or applying effects such as filters, blurs, opacities, things like that. And then the final step is drawing the quads, which are like, you should probably just think of them as like drawing all of the final textures that are the outputs of the final surfaces onto the screen. And so this is actually not done in the same process as Blink. It's done in the browser process via something called the Uber compositor. And it's called the Uber compositor because it's actually another instance of the compositor that draws not just the web page contents, but also the things around it, like the tab, the icons, and the Omnibox bar and all that stuff in the browser. Yes, Steve. The quad corresponds to like, think of it as like a final piece of texture after you've like taken the tiles and like passed them through all the surfaces you need in order and render passes in order to get them ready for the screen. So for example, you have like a layer with rounded corners, you have the mask layer and the thing, and then those intersect, and then those are in a thing, which is basically a bitmap that's been cut off, and then that thing is like a quad. You can think of it as like a quad. And apologies to super duper experts if I'm saying it all wrong. But basically that's what's happening, is that you're making intermediate pictures that are more and closer to the thing that you want on the screen. But the important thing here is that even after raster, there's more stuff to be done, basically on every frame. And so in theory, or in general, there can be cases where that actually takes a lot of time to execute. If you can generate pathological situations where you actually have to do a lot of these surfaces, even though you're not rastering anything. But they're not common. Okay, so let's go through some hard examples where things get a little bit crazy. And all of these examples basically have to do with the containing block. There are other examples using stacking context, which I'm not going to get into today. So here we have 3 divs. Seems simple. How hard can it be to paint 3 divs? So you have a scroller, a clipper, and a fixed position. The scroller is I guess I forgot to put the overflow scroll. You have a overflow scroll position relative div, and then below that you actually have a position absolute element that clips inside of a rectangle the children below it. And so as you remember, the containing block of the clipper is the scroller element because it's a positioning ancestor. And so the clipper element is both clipped and scrolled by its parent. Right? Yes? It's clipped and scrolled. Okay, so the fixed position element, however, its containing block is the root HTML element. And so it is neither clipped nor scrolled by the scroller. However, the clip CSS says that you should ignore your containing block and always clip everything. So what this means is that the fixed position guy is clipped by the clipper, but he is neither clipped nor scrolled by the scroller. So as you scroll, the clipper will actually move up and down, and its clip rect of itself will change as appropriate as it gets outside of the bounds of the scroller. And it will clip the fixed position element accordingly, like the clip on the fixed position guy will actually move up and down on him as you scroll the scroller. So this is super duper crazy, right? Why would you want this? We don't really. I would argue that no one really wants this. It's just an unintended side effect of well-intentioned additions to the web. So somehow you need to do this correctly. And if you actually go and like load this example on Chrome, in various cases we will do it wrong. Typically we do it wrong in the case where we try to composite things. For example, on a Retina Mac, this is one. Fixed position elements, we try to always make composited layers for them because that way you don't have to draw them when you scroll the web page. You just leave it sitting there and then you can scroll things under it. And it's very difficult actually to like reconcile that with the fact that you have a clip on this thing which is moving relative to some other composited layer. And these things have like kind of a weird interaction. The current design of the compositing system is kind of hierarchical in that we think of layers as like having a tree structure, similar to how we imagine the DOM has a tree structure, and we imagine Paint having a tree structure. And it turns out that in cases like this, it's not really one tree. There are like multiple things going on that need to be reconciled with each other. And so I told you I wouldn't really speak that much about Slimming Paint, but we actually are addressing all of these things head-on in the Slimming Paint design via these things called property trees, which are representing the different ways in which hierarchical relationships occur differently. And then breaking things into little chunks that maybe can be composited. So in this case, you really cannot just like composite the fixed position thing and then all will be well. It's actually going to be incorrect. You have to think carefully about what's going on and apply additional layers or give up in some cases. And as you can imagine, other browsers also often are actually incorrect in some of these cases. So here's, well, let's collect just some problems. Let me check the time. I think we're in good. So even if an element scrolls, even if an element does not scroll, sorry for the typos, even if an element does not scroll, it can be clipped by elements that do scroll. So that's really the point of that example, and it's just crazy things happen. And in place of that clip, by the way, you can also imagine doing like opacity or filters or something. It actually doesn't matter. All of those things are like crazy and messed up. And actually, they can be more messed up. So we'll see an example in a second. Border radius. Border radius, you know, you had to make that mask thing, but that seems doable. And what else could be wrong with border radius? So border radius, yeah. So let's do an example. So border radius with non-1 opacity child where some escape the clip. So this is similar to the previous one, where you have a fixed position and absolute position. The fixed position is not clipped because it's, you know, the fixed position, the absolute one is, and then there's opacity. So the problem here is that normally when you do opacity, you want to like draw the things below and then apply the opacity. And this is super important in cases where those elements overlap each other. Remember that example I went through where you had the 3 stacked divs? If you apply opacity individually to those, it's going to be incorrect, because if you apply the opacity and then you stack them, those, like the way transparency works is that transparency is kind of like additive, and so it's not going to look right. It's going to look darker than it should in the places where those divs intersect. And so it's important when you apply opacity to apply it once to all the things, so that it's correct when they overlap. So in this case, however, there's different clipping going on. And so if you apply the opacity together to the fixed and absolute position things, the output is like a bitmap, and you can't tease apart the fixed and the absolute guys anymore. And so how can you clip one but not the other after you've already done that? So you're screwed. So instead, really, you're basically forced to apply the opacity separately And this is like a corner case where it's actually a bug in the spec, where it's like literally impossible to do things along the way. Or it may be impossible to do things in certain cases along the way that was intended. And so you just have to accept some sort of compromise. Okay, so yeah, you can be forced to apply opacity separately in order to have a reasonable rendering structure in certain bizarre cases in the presence of overlap. So a third example, here you have clip with descendants that have a blur where some escape the clip. So really this is like another variation on the opacity one. The interesting thing about blur is that blur can like change the size of a thing. What blur actually does is it like takes each pixel and like spreads it out in directions, right? And so if you take blur, it can make things bigger. And because it makes things bigger, you can easily imagine cases where it interacts in a weird way with clip. So all these examples you can look at and play with after the fact. I think it's very instructive actually to do so and think about them. Yeah, same goes for blur. So I will close by saying one more thing, and then we can have questions. It's unfortunate that these things happen, but the containing block concept and the way it interacts with clip actually does have useful use cases on the web where you want to be able to escape the clip. Obviously, I think none of these weird examples we went through today are actually ones that you would want. And there actually are some proposals being considered maybe to avoid these corner case situations. And we've actually come up with some of these proposals. So if you're interested in them, I'm happy to talk about them afterward. So that's it. I think we have only a couple of minutes left, but we should do questions. Yes, Stephen.
In your first bizarre example with the clipper and scroller and all that,
yeah.
How does it render in other browsers?
The one where you had a clip with a fixed position thing below it?
Exactly, yeah.
It's broken.
Okay. In the same way that it's broken in Chrome, or in different
ways?
Okay.
Like Firefox fails to clip the fixed position thing entirely. On this screen, Blink applies a clip, but then forgets to offset it by the scroll if it's composited. If it's not composited, then I think it actually does the right thing. Blink does the right thing, yeah. And I'll point out that Safari, broadly speaking, has exactly the same bugs as Blink because their compositing integration structure is the same.
Thanks.
Yeah, Steve. There's a...
Do you have any sense of how much pain these things are actually causing web developers? You mentioned the containing block is useful, but all of the specific cases where we're broken, I guess we've always been broken and other browsers are broken, so do they care?
I think it's fair to say that there are a number of broken cases in the compositing integration that are not necessarily as weird looking as this, and so maybe they're not doing them, but they still happen. For example, I think it's very common that you might apply a border radius to an element, but you don't composite that element. You instead composite some child because, I don't know, you have the border of a widget and then there's a video in the widget, and maybe the video is clipped or something. The corners currently, in certain cases, do not actually clip the video. So I think basically when you try to like get more advanced, you often will hit these bugs because of these kind of things. But in general, like from the point of view of like the Paint team, for example, I don't think it makes sense for us to like implement it wrong, or implement it in a way that can't be done correctly, because maybe these examples are unreasonable and no one would ever do them, but there are other examples where you sort of need the same concepts, where it actually is kind of reasonable for the developer. So. Okay, thank you for coming.